Well, good morning, good afternoon, good evening, dear participants of our conference. First of all, do you see and hear me well?
Yes.
Okay. Let us start. We will talk about derivations and automorphisms of some important associative algebras of infinite matrices and related Lie algebras. Let us consider an associative algebra over a field and let us denote by symbol A minus the related Lie algebras, and let us recall some definitions. A linear mapping is a derivation is the product role on the slide holds. And also the commutator with a fixed element is an inner derivation of the associative algebra and the related Lie algebra. And a linear transformation star of the associative algebra A is called an involution if the conditions on the slide take place. We also denote by symbol K of A and star the skew-symmetric, the subspace of skew-symmetric elements, and this subspace is a subalgebra of the related Lie algebra. One more definition. Let us denote the by symbol J of A the group of invertible elements of associative algebra with unit, and also for an arbitrary invertible element, the conjugation is an inner automorphism of the associative algebra A and hence of the related algebra. We will talk about the following classes of algebras of infinite matrices. Well, let us consider an infinite set I, and the first example, we consider the associative algebra of I times I matrices over the field F having finitely many non-zero entries in each column. Let us denote such algebra by symbol M of I and F. And we will remark that if V is a vector space over a field F of the dimension which equal to the cardinality of the set I, then our algebra M of I and F is isomorphic to the algebra of all linear transformations of the vector space V. Also consider the corresponding related Lie algebra. Let us denote by JL of I and F, and the group of all invertible element of our algebra of matrices having finitely many non-zero entries in each column. The next example is the following. Let us consider the algebra of all linear transformations of finite range of our vector space V and related to the algebra. In the following example, we consider the associative algebra M sub RCF of all I times I matrices over a field having finitely many non-zero entries in each row and each column. Such algebra gives rise also to the corresponding related Lie algebra. We will denote it by JL sub RCF and the group of invertible element, but such that this element and its inverse lies in our algebra, because it may happen that an invertible element lies in such algebra, but its inverse doesn't. The next example is the associative algebra of I times I matrices over a field having finitely many non-zero entries. Sometimes such matrices are called finite matrices. And let us notice that this algebra, the algebra of finite matrices, is an ideal in the algebra of matrices with a finite number of elements in each row and each column. And the algebra of finite matrices and the algebra of matrices with finite number of elements in each row and each column depend on the choice of basis of our vector space V, the dimension which is equal to the cardinality of the infinite set I. Also, let us consider the correspondent related algebra, because our algebra gives rise to the related linear general Lie algebra, which is denoted by symbol JL sub infinity, and the special linear algebra SL sub infinity is a commutator algebra of JL sub infinity, and consider the group of invertible elements of our algebra M of I and F that differ from the identity element by some finite matrix. We would like to remark that both the algebra and their representation attract considerable attention in the paper of Vera Serganova, Ivan Penkov, Karl Hermann Knepp, Ivan Dimitrov, and others. In the case of characteristic of the field not equal to 2, the algebra of finite matrices is equipped with the transpose and the symplectic involution, so it gives rise to the Lie algebra O sub infinity and O sub infinity of skew symmetric elements relative to the transpose, and to the Lie algebra SP sub infinity of skew symmetric elements relative to the symplectic involution. And the last example is the algebra of Jacobi matrices over a field F, that is that Z cross Z, Z is the set of all integers, so we consider Z cross as matrices having finitely many non-zero diagonals. We means that matrices with the properties on the slide. And we also consider the corresponding related Lie algebra, which is denoted by symbol JL sub J of F. And remark that such Lie algebras found applications in the theory of solitons, and they are found in the paper of Boris Fagan, Boris Sigan, and others. Well, the problem is to describe automorphisms and derivations of associative and related Lie algebras of our examples. This result is based on the paper recently appeared online on the slide. So, first of all, we will talk about derivations of such algebras, and theorem 1 solves the problem for an associative case. And first, an arbitrary derivation of algebra of finite matrices is the adjoint derivation by element from the algebra of infinite matrices having finitely many non-zero entries in each row and each column. And second, an arbitrary derivation of the algebra of all linear transformation of finite range is also the adjoint derivation by the element from the algebra of all linear transformation. And the third, all derivations of the algebra of matrices having finitely many non-zero entries in each row and each column, and the algebra of Jacobi matrices are inner. The next problem is to describe derivation of Lie algebra of our examples. In this regard, we would like to notice that Carl Hermann Knepp in 2005 described derivations of special Lie algebra as L sub infinity, O sub infinity, and SP sub infinity over a field of characteristic zero. And he showed that every derivations of this algebra is the adjoint derivation by an element from the Lie algebra of infinite matrices having finitely many non-zero entries in each row and each column. And in 2018, Waldemar Golubovsky and Sebastian Żurek proved that every derivation of the Lie algebra of infinite matrices having finitely many non-zero entries in each column is inner. Well, the following theorem, part 1 and 2, extends Knepp's description to an arbitrary field of characteristic, but other than 2. And theorem 2, let field F has the characteristic not equal to 2, an arbitrary derivation of the Lie algebra as L sub infinity is the adjoint derivation by the element from the Lie algebra as JL sub RCF, Lie algebra infinite matrices having finitely many non-zero entries in each row and in each column. Second, an arbitrary derivation of the Lie algebra O sub infinity and SP sub infinity is the adjoint derivation too by an element from the subalgebra of skew symmetric elements relative the transpose and skew symmetric elements relative to symplectic involution, respectively. And the third, finally, all derivations of the Lie algebra JL sub RCF and the algebra of Jacobi matrices are inner. What can we say about the automorphisms of our algebras of infinite matrices? First of all, we begin with some remark. In 1975, Nathan Jacobson described automorphism of dense algebras of linear transformations of an infinite dimensional vector space, which is contained in a non-zero linear transformation of finite range. This description immediately implies the following result. The following statement is due to Jacobson, and it solves the problem for associative algebras. The first, an arbitrary automorphism of the algebra of finitary matrices is a conjugation by invertible element of the algebra of matrices having finitely many non-zero entries in each row and each column. Second, an arbitrary automorphism of the algebra of all linear transformation of finite range is of vector space V, which dimension is equal to the cardinality of the set I, is also conjugation by the invertible element, by invertible linear transformation of the vector space V. And the third, all automorphisms of the algebra of infinite matrices having finitely many non-zero entries in each row and each column, and the algebra of infinite matrices having finitely many non-zero entries in each column are inner. I would like to remark that for algebra of Jacobi matrices, the problem is open. We don't have a description of automorphisms of the algebra of Jacobi matrices. Some more definition which we need. The invertible linear transformation is called an anti-automorphism if the following formula on the slide holds. By the way, the anti-automorphism is an automorphism of algebra A with its opposite algebra. And the transpose transformations are anti-isomorphisms of algebra of finite matrices and of the algebra M sub RCF. We'll talk about it before. And latest that involution is just anti-automorphism of order 2. Well, in order to understand automorphisms of our Lie algebra, we need to understand anti-automorphism of associative algebra first, because every automorphism of Lie algebra either extends to an automorphism of associative algebra or is of the type of on the slide where star is anti-automorphism of the associative algebra. And the following statement is also due to Jacobson, and it describes the anti-automorphisms of the associative algebras. First, an arbitrary anti-automorphism of the algebra of finitary matrices and the algebra of matrices on infinite matrices, which is having finitely many entries in each column and each row, is a composition of the transpose and conjugation automorphism by invertible element of the algebra M sub RCF. And second, the algebra of all linear transformations of finite range of the vector space V and the algebra M of I and F of matrices having finitely many entries in each column do not have anti-isomorphisms, and these algebras are not isomorphic to their opposite algebras. One more remark. In 2001, Nina Stumme described automorphisms of the Lie algebras cell sub infinity or sub infinity sp sub infinity over a field of characteristic 0. And the following theorem solves the problem for Lie algebras a cell sub infinity or sub infinity sp sub infinity. And it says that Stumme's described extends for the arbitrary characteristic other than 2. So the first, let's characteristic of the field is not equal to 2, and the first, an arbitrary automorphism of the Lie algebra a cell sub infinity is a conjugation automorphism, or an automorphism of this of the type on the slide, where we use the invertible element of the algebra of matrices having finitely many non-zero entries in each row, in each column. And second, an arbitrary automorphism of the Lie algebra O sub infinity and respectively sp sub infinity is conjugation automorphism by invertible element X of the algebra of matrices, as I told before, having finitely many non-zero entries in each row and each column, where X multiplied by its transpose belongs to the field F on the slide. And the last theorem solves the problem for others example of Lie algebras of infinite matrices, namely the general linear Lie algebra JL sub RCF, and related algebra of the algebra of linear transformation of finite range, and the general linear Lie algebra JL of I and F. And the first, an arbitrary automorphism of the related Lie algebra JL sub RCF is a conjugation automorphism, or is automorphism of some special type on the slide by the invertible element of the corresponding associative algebra. And second and third part says that an arbitrary automorphism of the related Lie algebra of all linear transformation of finite range and the Lie algebra JL of I and F is also conjugation automorphism of some kind, where the conjugation is by invertible element from the algebra of JLV and from the corresponding associative algebra JLV and JL I and F on the slide. That's all. Thank you for your attention, and thanks again for all participants of our conference, for your participants.